Welcome to our lecture Fundamental of Casting and Solidification. Today is 7th lecture. We are starting pouring systems. In last lecture, we have seen the designing of core, pattern and mold systems. Now we are going to design mold detailing of designing of mold, where gating system will be there, different kind of gating system will be there, how to design a gates, sprue designs and all we will going to discuss in this lecture week. So, this is the conventional basic component of simple gating system for a horizontal parted mold, where we want to cast a product. Okay. This is in mold, we have made a pouring cup, this is known as pouring cup. Then this is a sprue, some people also name down sprue, down gate kind of thing. Then there is a bottom edge, there is a chances that we make a sprue base, some places it mentioned that a sprue well also, bottom well also, bottom base also. Then there is a runner, this is a runner. Okay. We say this is runner or cross gate, and there is a last part is called runner extension. Okay. And there is a in gates, there are 3 in gates or gates which are in between runner and casting. Now we will understand this all these terms and what is the use there, we will understand here. Okay. Gating system is conduit network through which liquid metal enters a mold and flow in the fill mold cavity, where the metal can then solidify to form a desired casting shape. So, first is pouring cup. Pouring cup or pouring basin, there is another name is called pouring basin, is the first part of gating design, where receive molten metal from the ladle. Okay. Molten metal from the, we melt the metal or alloy or pure material in the furnace, then this we bring to the casting and we pour. So, first part we pouring start in pouring cup and pouring basin. Pouring cup provides a steady flow into the sprue. And what is sprue? Sprue is vertical passage, this is called vertical passage. This part is called sprue, which is a vertical passage carrying molten metal downward. Okay. A sprue carries liquid metal down to join one and more runners. Okay. Usually the shape of this is tapered to avoid air aspiration. We will understand air aspiration in few lectures, after few lectures. So, just one way we can say the air attracts to the molten metal. To avoid that, we have to make tapered kind of sprue. Okay. You will understand in detail why we need a tapered or some other shape, not a straight. Okay. A sprue well or a sprue base located at the bottom of the sprue, it reduces velocity and the turbulence. It reduces the very high velocity, it reduces, so turbulence can be avoided. In this flow phenomena, we have tried to avoid turbulent flow. Okay. Otherwise, it will be very difficult to get a sound casting. Next is runner. Runner is a horizontal channel that distributes liquid metal into the casting, and there is a last part is called gate and in gate, that is last opening path where molten metal actually enter into cavity. In some castings, runner is behave as in gate also. Some pattern designs or casting design, they will know in gates. Runners behave as a in gates. Like you can assume that a simple casting loose piece pattern, single pattern. This is our mold cavity. This is a pouring cup. This is pouring cup, a sprue, and they know runner. This sprue behave as a runner as well as directly connected to, and they know ingates also. This can be also happen in lots of castings. So, runner and ingot can be replaced by a direct sprue or ingot without runners, like another I can show. Okay. There will be no ingot, this is runner, but there is no ingot, but there is no gate and ingots. So, without that also we can do casting. So, in this flow phenomena, mold filling of fluid, molten metal is going to flow. So, there are three principles it is going to use to understand the phenomena, how mold filling cavity, a mold filling happens in the casting. So, first is Bernoulli principle or Bernoulli theorem. Bernoulli theorem suggests at any point in the system, the sum of flowing liquids potential energy, kinetic energy, pressure energy and frictional energy is equal and a constant. The summation of at any point, the summation of these four energy will be same. The energy conserved, directly saying energy conserved. Okay. If some places something is increasing, like kinetic energy increasing, so other energies have to decrease because it is a constant at throughout the channels. Okay. It relates pressure, velocity and elevation along the flow line of flow, and this theorem is used for the gating design. So, Bernoulli theorem suggests Wz, you will understand this term in detail, Wz plus W V square by 2g plus W P by rho g plus W into F equal to constant. Okay. Let us assume you are following in these channels. Okay. In different gates are there. Okay. Point 1, point 2, point 3. So, what it is saying, Wz1 plus W V1 square plus 2g plus W P1 rho g plus W F1 equal to W Z2 plus W V2 square by 2g plus W P2 by rho g plus W F2 equal to W Z3 plus W V3 square by 2g plus W P3 rho g plus W F3. At any point this summation will be same. It is there chances that some factor will be same throughout the channel and some will be higher, so other factor should be decreasing in order so that it can give a constant value. Let us assume in a cross section Z and F are constant along the path 1, 2, 3. So, what happened? Velocity is increasing, then pressure should decrease. If pressure is increasing, velocity should decrease. You have to compensate that way. Okay. What is these terms? W is the total weight of flowing liquid, Z is the height of the molten liquid, P is the static pressure in liquid, rho is the density of molten liquid, V is the velocity of molten liquid, F is the frictional head loss. Okay. So, what is it written? W Z plus W V square by 2g plus W P by rho g plus W F equal to constant, we can take K. Now, we can divide W on whole side, which is a constant value, because we take mass weight of the liquid flowing in for a given casting is fixed. So, we are dividing by W. So, Z plus V square by 2g plus P by rho g plus W equal to K dash, that is again constant, right side hand side is again constant. So, this term written like this. So, what is happening in previous term, it was written in energy, it is written in terms of energy. Now, this term converted into heads or length scale. Okay. So, what is Z? The Z representing potential head, potential energy head. Okay, V square by 2g is kinetic energy or velocity head, velocity energy head. Okay, P by rho g, that is pressure head. Okay, pressure energy head. F is frictional loss of head, frictional energy head loss. Okay, the limitation we are applying something, but reality is different. Okay, since sand is porous medium, mold is our sand mold. If metallic mold, there is nothing to porous, we assume that, but in sand reality is that is porous, permeable material. So, but where is a limitation? The above equation assume an impermeable wall around the flowing metal. Okay, around the flow we assume that wall is impermeable. Okay, there is no porous flow, any outward flow is happening in pores and all. Okay, we are assuming that. In sand founded practice, mold medium can introduce problems such as air aspiration in the flowing liquid. This permeability can produce problems. So, we avoid this assumption, we put some assumption to maintain this equation, to use this to calculate filling time. Okay. So, these are the assumption. There is, let us assume we will understand this phenomena properly. This is our gating system, this is pouring basin, sprue well, then runner and runner extension, and some are ingate. Okay. 3 ingates are shown. There are lots of ingate can be developed. Okay. As you are pouring, the potential energy obviously at a maximum at the highest point in the system, top of the pouring system, pouring basin. What will the maximum? The potential energy will be maximum. As the metal flow from the pouring basin to the sprue, due to potential energy is converted into kinetic energy as stream increases in velocity due to gravity. Okay. Potential energy converted into kinetic energy due to gravity. As a sprue is filled now, then pressure head is developed. Okay. As a sprue is filled, then pressure head is developed. Now, once your liquid, once the flow in mold system is established, when all things are filled one time, then the potential energy, obviously the position we are pouring is fixed. So, potential energy Z and frictional loss head become virtually constant, mostly become constant. We assume that they are not changing too much with time, but so the condition within the gating system design are determined by the remaining factors. There are 4 factors. One was potential head, kinetic energy head, pressure energy head, and frictional loss energy head. So, friction and potential become constant in the gating system, gating and runner system, when the liquid is already filled. So, what will happen? The potential energy and frictional loss fixed. So, what are remaining? Kinetic energy and pressure head energy are going to play your designing of the gating and runner system. So, if because summation of 4 was constant and 2 are already constant. So, what happened? If velocity is high, then pressure should be low, and obviously and if pressure is high, velocity should be low, and the velocity should and pressure should play a critical role to design our gating system. So, we can see pressure head and velocity at any given cross section is going to play main critical role for in the gate system. Now, we have applied Bernoulli equation, but we can't apply Bernoulli equation without any a proper assumption. We can't apply Bernoulli equation any place. There is some limitation. What the limitation is there? There is 6 or 7 assumption is there. First is flow should be a steady flow. We have to assume that flow properties like velocity, density and pressure at a given point must not change with over time. It is not a function of time. Okay. Incompressible fluid, second should be flow should be incompressible, means density should be not varying with pressure and remain constant throughout the flow. Okay. Third is ideal and non viscous fluid. We assume that fluid viscosity is assumed to be 0. Fluid viscosity is assumed to be 0, meaning internal frictional energy frictional, internal friction and energy loss due to viscous forces are negligible. The internal friction and energy loss due to viscous forces are negligible. You have to assume that. Fourth, flow should be irrotational. The fluid particle must not experience any rotational or angular velocity around their center of mass. We assume that also. Fifth will be flow along the streamline. The theorem represents the conservation of energy and strictly applies to a single streamline rather than across multiple streamlines. Okay. No work and heat interaction. There should be no energy added and removed from the fluid by external mechanical devices or heat exchanger during the fluid flowing. Okay. And obviously, if there no energy added and removed, so we have to assume that there no heat transfer is occurring during that process. During the mold filling in gates, we assume that there no heat transfer is occurring. There are 7 assumptions: steady state flow, incompressible fluid phenomena, ideal and non-viscous fluid, irrotational fluid, flow along a streamline, no work and no heat transfer should be occurred during the mold filling criteria. Next assumption is, next theorem, next principle is used for the understanding of fluid phenomena. We use law of continuity. Law of continuity suggests for a system with impermeable walls, obviously we have to assume that because we are going to use Bernoulli also, and incompressible fluid, incompressible rho is fixed, rho is constant. The flow rate will be same at all the points in the system. So, we can take a system where point 1 and point 2 and flow is happening in this direction. So, mass flow rate is written as rho A V equal to rho A V. V is the velocity constant, rho density, A cross section area, V is velocity. Okay. So, rho A V is constant since we are talking about incompressible flow. Rho constant. So, at given A and B, A1, B1, rho 1, rho 2, A2, B2, rho 1, A1, B1 equal to rho 2, A2 and V2, since rho equal to constant. So, rho 1 equal to rho 2, we can write that and it will convert into flow rate. A1 V1 equal to A2 V2 flow rate. It maintain flow rate at one place, is flow rate is A1 V1 is should be equal to A2 V2. Second theory should be law of continuity. Third, in the mold filling we apply third fluid flow principle is momentum effects. We have to, third is momentum effects. Newton's first law states that a body in motion will continue to be in move in given direction until some force is exerted on it in change in its direction. Okay. So, if we are going to work, so if inertia force is rho A V square scaling, viscous force is mu V L into A, and the ratio of inner force divided by equal to rho A V square mu V L A cancel out, V cancel out, rho V L by mu as known and the ratio of inertia force divided by viscous force is known as Reynolds number, which is equal to rho V L by mu. Rho is the density, V is the velocity, L is the characteristic length scale. For a circular pipe, L will equal to D, okay, and mu is the dynamic viscosity of the flowing liquid, okay. And it suggests that if Reynolds number is less than 2000, then the flow is characterized as a laminar, means with the molecules of the liquid tends to move in a straight line like this. If at this position is particle is here, after some time it will be same height and same position along the depth, and it will just move in one direction. It is not going to do zigzag kind of thing, okay. That is called laminar nature, okay. If Reynolds number Re less than 2000, which Reynolds number is the ratio of inertia force by viscous force, okay. So, what is happening in this fluid particle is moving in a straight line, okay. If your Reynolds number is between 2000 to 20,000, this is the most common practice we observe in the casting, okay. This is the most common range. Range is in casting is it is most popular. In casting, it is very difficult to get laminar, but we have to avoid turbulent, okay. First thing we have to avoid turbulent, but we can't get laminar also, okay. So, what you have to need? What you need? The range transition regime, where laminar to transition happen, that range is 2000 to 20,000. This range, some mixing and turbulence will occur, but a relatively undisturbed boundary layer will be maintained on the surface of the stream. So, there is some zigzag will happen in the flow, but not that much as a turbulent nature, okay. It can be considered relatively harmless as long as the surface is not ruptured, thus avoiding air entrapment in the flowing stream, okay. Let us assume your Reynolds number is more than 20,000, this is called turbulent regime. Turbulent regime, if your Reynolds number is more than 20,000, we say it is a turbulent regime. If your Reynolds number is more than 20,000, the flow will severely affect the in turbulent regime. This will lead to rupturing of stream surface with a strong likelihood of air entrainment and dross formation as flowing metal reacts with gases. If what will happen if your flow is very turbulent, and why it is very common in casting range more not laminar. So, let us assume water and there is a molten metal, okay. The calculation of Reynolds number, and let us assume L is equal to V equal to 1 meter per second, okay, meter per second, okay. For water 1000, V is 1, L is 1 meter, let us assume 1 meter is there, L is 1, what is viscosity? 0.001, 10 to power 6, okay. That range we are going, okay. But what happened with molten metal? Same thing, Reynolds number 7000, because metal has density is high, other it becomes 7 times higher because of density, okay. Density is playing another role. So, what happens even we do casting, like assume if your length scale is small and velocity is small, the casting become in casting density is high, like aluminum is 2.7 time of water, whatever value you get in water, it become very high, like 2.7 or 7 time higher in the casting because of density into 1 into 1, let us assume 0.003, So, it 2 into 10 to power 6, 2 times higher than water, okay. But length scale is generally in not in meter, it is around half meter or cm scale. So, it can be lower than that. So, you can see if you are going metallic systems, what is happening, even viscosity is higher, but not that much higher. Obviously, the density is higher in metallic system, casting has more and more turbulent behavior. So, what happens if we are not able to achieve laminar, we are not able to achieve laminar kind of flow in casting for more than 20,000, the flow will be severely turbulent. Okay. If your Reynolds number is more than 20,000, it is happening. For example, also we can see if you are taking length scale same, if you reduce your length scale like into 4 point, length scale and velocity can be lower. So, it can reach 2000, then even that situation we will see casting, metal casting has higher and higher Reynolds number due to density, okay, density property. This will lead a rupturing of the stream surface. So, what happen if your flow is turbulent, what will happen? It is able to break the sand mold, rupture the mold surfaces, okay, with a strong likelihood of air entrapment. What happens when you are breaking the mold? There is chances that you will attract gases from the outside and air will be, what will happen with air? If air will come and hot metal is there, what will happen? Reaction will happen, Fe and oxide, Fe2O3 will form, aluminum plus oxide, aluminum oxide will form. So, it is different from the our requirement, and dross formation as following metal reacts with gases. Okay. So, these are the 3 principles. Based on that we design our casting casting design, mold filling design. First is Bernoulli principle, second is continuity equation, third is momentum effects. We have to maintain our Reynolds number less than 20,000. We have to try to that. We can't go laminar. So, we have to try that. We can go Reynolds number less than 20,000. First, Bernoulli principle we have to use. So, pressure and velocity, if your mold filling is completed. So, for the design of gates and runner, the main play will be between the pressure versus velocity. Okay. Third is law of continuity, we have to assume that wall are impermeable. So, what happened? You are maintaining law of continuity, flow rate is constant at the all the places. Based on that, we are going to design our getting designs in next lecture. Thank you.